Hello, in this video we're going to talk briefly about separation of variables and mainly executing this with an example. So let's say that we want to perform some integration, a solution method for this differential equation. dy dt equals quantity t y squared. Now the issue that we're going to have is if we try to integrate both sides dt right now, the left side will be fine because the integral of the derivative is simply the original function, which would be y. The integral of the right-hand side, however, involves both a t and a y. And the thing we need to remember is that y is a function of time, so we cannot treat y as if it were a constant. So we're kind of stuck. So the strategy is, first of all, let's try to get any components, any factors involving y over to the other side. So notice that this is a multiplication problem over here on the right-hand side. So if you take ty squared, that means t times y times t times y, which you have two factors of t and two factors of y. And you know the shortcut usually is we square the first factor, we square the second factor. Okay, so I can get y squared over via division, right? Because it's a multiplication problem, so I can divide it over, and now I have 1 over y squared dy dt equals t squared. Having t squared over here is fine. It doesn't have to be a constant. We just want to make sure that the left-hand side, that's where all of our functions of y go. We want to make sure that on the right-hand side, that's where the functions of t stay, if there are functions of t. So now we can integrate. Okay, here's our integral. And here's the nice trick, right, that dy dt dt is, the dt's cancel, and you're left with the integral of 1 over y squared dy equals the integral of t squared dt. Okay, so now we can compute our integrals using some technology. Find out that the integral of 1 over y squared is negative 1 over 3y cubed, and the integral of t squared is 1/3 t cubed plus c. And just check our work. If we want to take the derivatives of these two, make sure that we get t squared. We do. 1/3 t cubed, its derivative is 1/3 times 3t squared plus c. The derivative of that is 0. And we can just double check, make sure that works out. Okay, so my last step is I've actually solved the differential equation, but this is not very useful because usually when I want to do things like I want to graph it, I want to be able to plot it, do some analysis of this function. So what I'm going to do is I'm going to try to solve for y. This may look a little tricky, right? Because we first of all have to get the y cubed out of the denominator. Well, one little tactic that we can use other than multiplying both sides by y cubed and then having to flip-flop things back and forth is I really just want that to appear in the numerator. So I can actually take the reciprocal of both sides and they're still going to be equal to each other. So think about the numbers 1/2 and 2/4. So I won't write it down here, but if you take 1/2 and you take the reciprocal, you get 2 over 1. If you take 2/4, which is the same as 1/2, and you take the reciprocal, you get 4 over 2, and 4 over 2 is 2. So 2 over 1 and 4 over 2 are equal, and so are the reciprocals 1 over 2 and 2 over 4. So what I'm going to do here is I'm just going to take the reciprocal of both sides. I have to do it to both sides because the reciprocal of this side will equal the reciprocal of this side. So 1 over this will equal 1 over this. And so if I take 1 divided by a fraction, I can multiply by the reciprocal of the fraction. And let's see here. I don't know what happened to... there we go. Okay, so here I will just end up with negative as my negative sign, 3y cubed. So that's the reciprocal of 1 over 3y cubed. Maybe I'm doing too much notation here, but basically taking the reciprocal of this side I have to do because I can't just put everything on this side under 1. I can't just do 1 over 1/3 t cubed plus 1 over c. It's 1 over all of this stuff, right? Because I'm doing 1 over this side and then 1 over this side. So now I've got y back in the numerator, and now I just have to get rid of the -3 coefficient and the 3 exponent. So I'm going to do that next. Okay, so how do I do that? Well, I'm going to divide both sides by -3, or you can think about it as multiplying both sides by -1/3. Cancels out the -3 here. And now I'm going to take the cube root of both sides to get y to the first power. And also what I'm going to do is because I have a fraction times a fraction, I can multiply the 3 into the denominator, which will give me just t cubed. And then remember, when we multiply an arbitrary constant by another constant, we end up with just still the arbitrary constant. So I take the cube root, and I have -1 over t cubed plus c. Now you got to be real careful. You cannot just willy-nilly move the c out of the denominator, because dividing by a term involving c is different than just simply adding a term involving c. So you can't move that over here. You can't leave it in the numerator. It's got to follow that 1/3 t cubed plus c. Okay, so this is our final answer. At this point, now we wanted to we had an initial condition, like a value for t and a value for y, then we could figure out what the value of c would need to be in order to achieve that initial condition. So at this point where we've completed the problem, we don't really need to simplify this any further. There's no point. And no, the negative does not really create a problem down here because it's still possible that the denominator could be negative, and so a negative divided by negative would be positive, and this is a cube root, so it wouldn't matter anyway. Alright, so there's our final answer. So when does this method not work? Well, we're going to find out later on that this method doesn't work when the right-hand side contains functions of y and t that are being added together. Okay, so this is an additive right-hand side, and you can't simply divide by y on both sides, because if you do, you'll end up with y plus t over y, which is y over y plus t over y, and so even though you got rid of one of the terms involving y, now you introduced it as a denominator for t. Same thing here, ty plus 1. Well, we do have t times y, but the problem is if I divide both sides by y, then I'm going to be stuck with 1 over y. If I divide both sides by y plus 1, well, that's still going to be an issue because the t can't be factored out from 1. Same kind of idea here. The problem here lies in the denominator because I have an additive set of terms, and there are situations where the model is additive, like this, but where you can tweak it enough to where you can turn it into a product involving one function of t and one function of y. So dy dt equals ty plus t can be done using this method, because notice that I can factor out a t from this term, and I can factor out a t from this term, and I get dy dt equals t times quantity y plus 1, and then I can divide the y plus 1 over and kind of proceed as usual.